Hi, my name is Enzo Spera, and I'm going to present my work on the optical properties of methylammonium lead halide perovskite. We study the optical properties as a function of temperature, and we see some changes due to the initial process of degradation that we are going to present here. First, let's talk about the samples. So the samples were prepared by a two-step process. First, we put the solution, the precursor solution, on spin coated, and then we added chlorobenzene as an antisolvent. And finally, we anneal it for 10 minutes on a hot plate at 100 Celsius degree. These samples were studied in a closed cycle helium cryostat. We put the samples inside the cryostat with quartz windows, and we measured the transmittance and the photoluminescence of the samples every 10 Kelvin from room temperature to 12 Kelvin temperature. So to do these measurements, we can see here the small picture of the device we use. This is the cryostat. We use a tungsten lamp to measure the absorbance, and we use a blue for 55 nanometers LED to stimulate the photoluminescence. Outside of the cryostat, before to coupling to the spectrometer, we put a 550 nanometer filter to took away the remaining blue light from the LED and have a better signal for the photoluminescence. We analyzed the absorbance spectrum with the Elliott formula for exciton absorption and use a Gaussian function to modulate the photoluminescence. We repeat the measurement 3 days with 6 days apart each one, and we store the samples in a low vacuum. The handling of the samples were made in a 40% relative humidity atmosphere, so the degradation due to humidity can be mitigated. After the 3 days of measurement, we can see that these diffractograms shows the presence of this subproduct of the degradation, that is iodine lead iodide, sorry. So many things have been studied about the degradation mechanism of methylammonium. Particularly have been shown that humidity degrades the sample. That's why we take care of work in a low humidity environment. But also have been shown that not only UV light, but also blue light can degrade the samples. This is because the blue light can take electrons to the antibonding of the nitrogen-hydrogen bonds in the methylammonium. These bonds should thermalize. These electrons should thermalize, but there's evidence that they don't, and that these bonds break, leading to these subproducts, hydrogen and methylamine. These two subproducts are gaseous and volatilized, leaving vacancies inside the material. These vacancies lead to a change in the oxidation stage of iodine, so we end up with the formation of lead iodine. This is observable here in this diffractogram in comparison with the initial diffractogram of the sample right after its manufacture. We observe that here the biggest changes in the samples due to the degradation that are associated to the photoluminescence. we can see that the photoluminescence of the sample initially have a narrow spike right below the position of the band gap, the exciton band gap. And in the lowest temperature, about 80 Kelvin and lower, we see a second spike of photoluminescence that is wider and with a lower energy. This second and lower energy peak increases intensity and quenches the intensity of the higher energy peak. And this behavior become more strong for each day of measurement. Here we can see the position of the excitonic peak of the absorption in red. The band gap of the material is in blue here, and the photoluminescence peak is in green. Finally, in pink, we have the second photoluminescent peak that increases his presence and changes his behavior for the successive days of measurement. This also allows us to see where the phase transition from tetragonal to orthorhombic phases is located at initially 110 Kelvin, then 125, and finally for the third day at 140 Kelvin. So the degradation process has moved the position of the phase transition, but also moves changes the intensity of the photoluminescence spikes. Here we can see the integrated photoluminescence for the both photoluminescence peaks. For the first day, the lower energy peak that is here is this one, has an integrated intensity comparable to the higher energy peak, but only at lower temperature, at temperatures lower than 50 Celsius, 50 Kelvin, sorry. For higher temperatures, we can see that the higher energy peak domains the photoluminescence. And also it's possible to see that for the orthorhombic phase, the photoluminescence is quite strong in comparison to the tetragonal phase. For the successive days of measurement, we can see that the low energy peak has quenched the high energy peak, and this behavior continues to the third day of measurement. When we compare the integrated photoluminescence, we can see that the low energy peak has considerably stronger intensity than the high energy peak. And this is also true for the third day of measurement. So we analyzed the behavior of the photoluminescence with the Guglielmi model and a model for localized recombined model. And we have seen that the high energy peak, which is this one, and this one, have a free excitonic behavior, but the lower energy here have a localized exciton behavior that indicates that the excitons are becoming more and more trapped with the degradation process advances. This is probably associated to the generation of vacancies. As we can see here, in red and blue, the absorbance properties of the material have not changed quite a lot. This is because perovskite are known for a strong tolerance to defects, but it is possible to see in this photoluminescence measurement that these defects are changing the photoluminescence behavior. These trap states generated due to the increase in vacancies is generating traps that are trapping the excitons, reducing its energy and changing its behavior that leads to this recombination due to localized excitons. So finally, a small resume of a small the conclusions of this work then are that the initial degradation process due to the intense blue light generates vacancies in the material that change the position and temperature of the phase transition and also quenches the free excitonic recombination that give place to photoluminescence and starts a second mechanism that is localized excitonic recombination that leads to a photoluminescence with a lower energy that is showed up here, here, and here. Thank you very much.